have today we have two things. First, we have to look at the similitude or similarity in turbo machines, and then we will start to study the axial flow compressors and fans. So let's go to the similarity first of all. Why do we use similarity? We use similarity or similitude to match what we are measuring in laboratory to real life case. And in order to do this, we do the dimensional analysis. So in your fluid mechanics course back in your bachelor's, you remember this dimensional analysis, and there you were using some non-dimensional numbers like Reynolds number, Mach number, and etc. So there, what we were using was the Buckingham pi theorem, if you remember this theorem in here. So what was this Buckingham pi theorem? Actually, it said that if there are n numbers of variables and m number of fundamental units, so these are fundamental units, the equations relating these variables can be collected and expressed as n minus m number of dimensionless numbers. So this is not n equal to m, this is n minus m. Let me write it in here. It is n minus m, not n equal m. So what are the fundamental units in here? The fundamental units, you remember from your, again, fluid mechanics, there were mass, length, time, and temperature in your fundamental units. So these are the units that you cannot break them, the mass and length and time and temperature. So why do we do this non-dimensional analysis? We do this because when we use this approach, a group of variables representing some physical process, they get reduced into a smaller number of dimensionless groups. So we are dealing with a smaller number of variables. And also, if we do laboratory testing, on scaled models, this non-dimensionalization makes our work easier, and also it becomes possible to do some testings inside the laboratory. And also we can do some unique representation of performance. So when you do this non-dimensionalization, for example, you can say that your performance of this aircraft is a function of altitude, is a function of Mach number, is a function of Reynolds number, right? So you can have a unique representation. So you remember the approach in non-dimensionalization was in two steps. First, you had to select m number of variables, which include a group of all fundamental units. So all fundamental units have to be there from the list of total n variables. And then you have to set up a dimensionless equation, right? Remember, you had to set up a dimensionless equation and combine these with each of the remaining variables. So how do we do it in turbomachinery, for example? In turbomachinery, we have some typical parameters, okay? What are these? For example, uh, in geometry of the turbo machine, you have a diameter of a turbo machine. The turbo machine that is rotating has diameter. And you have some blades on it. So these blades have some length or some chord length. Either of each these two you can use. And rather than geometry, you have operating conditions like the pressure, temperature at the inlet of the turbo machine, your mass flow rate, your rotational speed, which is in rounds per minute, RPM. And also you can have some properties according to your fluid, like the constant, gas constant R, and your kinematic viscosity nu, and your specific heat ratio gamma. So you have lots of these things, and you can express your performance of your turbo machine by something like this. So you can say that, okay, this turbo machine is increasing or decreasing my pressure, and this increase or decreasing pressure is a function of this. All of this mass flow, the pressure at inlet, your gas constant, your temperature at inlet, your specific heat ratio, your RPM, kinematic viscosity, diameter, and length, right? So, for example, if you use L1 for the blade height and L2 for the blade just chord length. So you can say that, let's say this performance of my turbo machine is also a function of all of these parameters. And now we are trying to make it simpler, much simpler and much simpler. How? First of all, let's combine R with T0 and let's write the combination in R and T0. So your pressure or anything can be a function of mass flow rate, pressure, RT0 and blah, 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 blah. And if you put the pressure inside this function, you can say that another function of everything is um, equal to 0, right? This is 0. So you have to note that your RT0 is actually in meter square per second square, so there is no value of temperature inside this RT0, so there is no need to use Kelvin for this. Another example of derived unit, not a fundamental unit, is a pressure. So pressure is not a fundamental unit. Pressure is expressed as mass times L to the minus 1 times T to the minus 2. So what do? We just presented some variables and we count them, these n variables. How many variables we have? We have 10 variables, right? And you have to take 3 variables having 3 fundamental units because you just have mass, you have length, and you have temperature, right? Sorry, time. So mass, length, time. So you take 3 variables. For example, right now we take pressure that has all these 3 inside. We take RT0 that has length and time, and we take diameter that has length. So we have 10 number of total variables. We took 3, so n minus m is equal to 7. This says that you should have 7 non-dimensional groups. So let's go to the first one. For example, you want to calculate the first non-dimensional group and you call it pi1. This is the pi Buckingham pi theorem. So you're gonna find all these 7 non-dimensional groups. So we said that you have to multiply these 3 that you selected before and just put one remaining variable out of those 7 variables. And you have to put the x, y, z, to the powers of these 3, and then find these x, y, and z as the unknowns of this equation. So you see that pressure is m L minus 1 T minus 2 to the power of x. RT0 is L2 T, L squared T to the minus 2 to the power of y. And diameter is length to the power of z. You have mass flow rate, which is the unit is mt to the minus 1. So this is equal to pi 1. So it means that if you just take the powers of x, y, and z, you will find these values for each of them. So it means that your pi 1 will be equal to what? This is p01 to the minus 1. So this is x here. rt01 to I mean the square root of rt01. This is your y in here. And again, and then you have this, which is your z in here. So your pi 1 is actually square root of rt01 over p01 d squared times m dot mass flow rate. So you call this mass flow parameter. So your mass flow rate times this is called mass flow parameter or MFP, right? And using the same procedure, you can find the rest of these non-dimensional, let's say, numbers, pi 2, pi 3, pi 4, pi 5, pi 6, and pi 7. And this is actually your homework, so you already are given all these non-dimensional groups. So as your homework, you have to find all of these pi groups. And you also have to note that these square root of gamma rt0, you remember that it is the speed of sound, so it is related to your Mach number, right? And this nd squared over nu is pi 7, nd squared over nu has somehow relates or represents your the Reynolds number to you. Okay, so now while we write all of these groups, so we have 1, 2, 3, 4, 5, 6, 7, 7 non-dimensional numbers. Now we can say that a function of all these non-dimensional numbers is equal to 0. So what is the benefit of this? The benefit of this is that instead of using, for example, mass flow rate versus the exit pressure of turbomachine, you can use mass flow parameter versus pressure ratio, and you can let's say give the variations based on this. So this is very good in terms of laboratory, as we said, because in the laboratory you're using a scaled model, and then because these are non-dimensionalized numbers, then you can use the same curve and bring it to your real life case, your real life turbo machine. Again, if you assume that your L over D, which is the length of the blade, or the chord length of the blade, is constant, then you can write this function as this. So you can take the pressure ratio out of this function, and you can write that the pressure ratio is only a function of mass flow parameter, right? This one is mass flow parameter. Your Mach number, as we said, your Mach number was this one related to this one. Your Cp over Cv, which is your gamma, and your Reynolds, and as we said, nd squared over nu is your Reynolds, and these two we assumed that they are constant, so we took them out. So this is the final thing that we obtained in here. So your pressure ratio is only a function of 4 things. Now let's go to the second part, that is actually the starting point of our real turbomachinery course, which is the axial flow compressors and fans. So you remember that you had compressors and you had two types of them. One was the axial compressor and one was the centrifugal compressor. And you know that in jet engine, you're gonna have both of those compressors, especially the axial compressors are mainly used, as you can see in here. So what is the idea of using a compressor? As you know, in a jet engine, you're taking air and you're compressing it and then deliver it to the combustion chamber, right? And then in combustion chamber, you burn the fuel and air that is compressed, and then take the energy of this and give it to the turbine. And then turbine runs the compressor, runs some other uh, things inside the aircraft, as well as delivering it as a jet and provides thrust force for you. So in the combustion chamber or in the combustor, you really need high pressure and you really need low velocity. That means low kinetic energy. But why? Because when you have high pressures, it means that you can do this combustion process more efficiently. And when you have low velocity or low kinetic energy, it lets the flow to evaporate and mix better. So if it is very fast, it cannot mix very good, and it cannot evaporate. So that's why you are trying to lower its velocity. Based on what you know from your aerodynamics and your fluid mechanics knowledge, if you have a very, let's say, not very, but if you have a low speed flow or low Mach number flow and you diffuse it, I mean, put it inside the diffuser, like what I'm showing in here. If you put it inside the diffuser, then its kinetic energy will drop, right? If the flow comes from here, from left to right, and it passes this diffuser, if its pressure is P1, its velocity is U1, and total properties are P01 and T01, then after passing this diffuser, you have a flow that its pressure is increased, so it is diffused. And let's say its velocity also is decreased. So its, let's say, kinetic energy is decreased. But what is happening if there is no loss, if it is implicit flow? So there is no boundary layer. It means that there is no loss. When there is no loss, it means that your total pressure stays the same. And if it is adiabatic flow, which could be, it's very normal that there is no, let's say, um, heat transfer to the ambient, so Q is 0, then your temperature, total temperature stays the same. But we need to increase the total pressure. Thus, this means that only by using a diffuser we cannot have a compressor, right? So this diffuser, at its, uh, let's say, when it is staying like this, not moving, not rotating, so it means that it's not doing any work on the fluid. So it means that it is not suitable as a compressor. So what do? We said that a fixed diffuser only gives rise to the pressure, right? Because it only lowers the velocity or kinetic energy. So you have to have a moving or rotating diffuser which does work on fluid to give rise to total pressure as well. And as you know, in this manner, by the action of diffuser itself, the static pressure rise happens inherently. So imagine that diffuser that we showed you in the previous slide, this diffuser in here that is rotating. So it is a diffuser, so it can what? Diffuse the flow, so it can raise the pressure. And it is rotating, so it does some work on the fluid, so it can also raise a total pressure as well. So what is basically happening in a one stage of compressor? You remember that one stage is like one rotor and one stator, right? Inside the rotor, you have rise in stagnation quantities. So it means that rotor is rotating and it is energizing the flow. And then rotor delivers this energized flow to the consecutive stator, and this stator keeps these stagnation quantities preserved and increases static pressure. So it diffuses the flow for you to increase the static pressure and decrease the kinetic energy for you. Two notes I'm giving in this slide. The first one is that we are, let's say, studying axial flow compressors and fans. We are not telling anything about the fans, but fans are just rotors. Okay, there is no stator. And without any divergent duct, they are not able to change the static pressure and velocity. So everything we are telling about compressors is applicable to fans. Only fans are just rotors. So you have to imagine only the rotor part in a compressor as a fan. And as another note, you have sources of losses when you are flying in a low speed flight. You have only friction as a source of loss, but when you have high Mach number, you have also shock waves that are a source of loss for you. Okay, now let's have some ideas. The first is that what is happening inside an axial compressor is that the flow pressure is increasing. But the stagnation pressure, the maximum amount that can be increased inside one stage, I mean inside one rotor and one stator, is limited and it's about 2. So you cannot raise this amount. Why? We already had this discussion before because it's very prone to stall. It's very because it is working in an adverse pressure gradient condition, so it's very prone to stall. So when you are increasing this pressure, something is happening that we call it as surge. So what is surge? Physically, it's like as I draw it in here, it's like putting a complete barrier. This is a complete barrier or blockage inside in front of the engine. So if the flow tries to go from here to here, as I sketched in here, this is a barrier, so flow cannot go inside and then turns back. Okay, this is called surge. So why surge is happening? When you have a set of blades right in here, these blades are rotating. When they get into a stall, and what does a stall mean? A stall means flow separates from these blades and they stall, right? When they get into stall, as you can see, these make like a barrier in here, the flow that is separated. So this makes this barrier for you. And this makes the turbo machine a compressor or whatever we have to surge. So this blockage is created and surge occurs. The axial compressors are very sensitive or prone to stall and surge, right? That's why we said that we cannot increase this amount. This is the optimal amount inside one stage. But on the other hand, you have centrifugal compressors that we will see them later. These are very robust and they do not stall because there is no diffusion there. So what is this diffusion? Actually, diffusion is the action of the diffuser, but we will see it in a short, in some slides next.